got some paper, very recent. You see it's current status of epsilon prime over epsilon, which is November 28. Well, actually, this is something what we are discussing on CP violation. So epsilon prime and epsilon parameters which describe CP violation. And let me add this to material of the previous lecture before we will start new stuff. So we discussed discovery of CP, CP violation, and it was discovered in the decay of K2 meson into 2 pions. K2 meson, as we discussed, has CP parity -1. 2 pions have CP parity +1, and therefore existence of such a decay certainly proves existence of CP violation. Now, what are possible mechanisms, at least at phenomenological level, of CP violation? Phenomenological and the description, let me write this. Because in the standard model we have a description in terms of quarks and W bosons, and I have already written some diagram which is responsible for CP violation. So CP violation may occur via mixing. So we have K2, again, so we are discussing the case of K2 into 2 pions. That's what actually shows the CP violation. So it may happen that due to some interactions, K2 can be transferred into K1. And then K1 can decay into 2 pions, pi plus, pi minus, or pi 0, 2 pi zeros, with CP conservation. So this is normal. So they have K1 has CP parity +1. And CP violation occurs here in this mixing of K2 and K1. So this we characterize the parameter which is proportional to epsilon, and epsilon is proportion something like 10 to the -3. So this is the level of CP violation. Of course, number of events observed was small, and the CP violation effects are 3 orders of magnitude weaker than just usual weak interaction decays. So this is the smallness of this decay, of the effect of CP violation. Second mechanism is direct CP violation. When we have transition of K2 immediately to 2 pions without any intermediate step, as it is here. So it turned out that this mechanism dominates. That was measured experimentally. And this one is subdominant. And it is characterized by epsilon prime parameter, which is, again, 3 orders of magnitude smaller than this parameter. And so the paper which I have just shown you, some new computations of this epsilon prime over epsilon. Well, in fact, it is not so easy to make computation because strong interactions are involved. So you need to take into account corrections due to strong interactions. Here we have hadron, and final state is hadron. So at long distances, strong interactions become important, and therefore it's not so trivial to make computations, even in the standard model. So existence of such a mixing means that matrix element between K2 or K1, Newtonian, responsible for this CP violation, and K2 is non-zero, right? Now we had expressions for K1 and K2 in terms of K0 and K0 bar. I will not reproduce them, you have it in your notes. So that's K1 is square root of, 1 over square root of 2 K0 minus K0 bar and K2 is K0 plus K02. Anyway, so if I insert here expression for K1 and K2 in terms of K0 and K0 bar, I will get the following: K0 H K0 bar minus K0 bar H K0 not equal 0. So here, actually, I will have 4 terms, but 2 cancel because of CPT. When I have here K0 and here K0 bar and K0 bar, these elements are equal because of CPT theory. Okay? So these 2 left, and therefore from this equality I will get this one, which can be written that these 2 are not equal. So I can put just one of these elements on the right hand side, and I will get this inequality, which is very important. What it says? It says the transition of K0 bar to K0 is not equal to inverse transition, K0 bar and K0. Okay? So that clearly means T violation. So if in the same setup, experimental, I produce K0 bar and find what is the transition to K0, that will not be equal to inverse transition. So it's clearly T violation. And since we assume CPT, that would imply CP violation. Well, I have written the diagram, box diagram, in last lecture, which actually shows this transition of K0 to K0 bar. Remember the diagram, I will not put details of this type. So K0 and K0 bar. And since in these vertices I have mixing parameters, right? I will get this inequality because these 2 matrix elements are connected by charge conjugation, right? And so since there is a complexity here, and I compute complex conjugation, it will be not equal to inverse diagram. So this is the origin of CP violation and the way it is related to complexity of mixing parameters. Another comment I want to make is that since this matrix element is not equal, so you have transitions, even in vacuum, between K2 and K1. This means that these states are not mass states once you have these transitions. So they are not eigenstates of Hamiltonian, right? And therefore, some other states, which are combinations of K1 and K2, have a definite masses. So that's what we call Ks. I already said this is K short. This is the state with definite masses, which is approximately K1, and K long is approximately K2. So this is terminology we are using, and actually mixing, so which means that Ks is the combination of K1 and K2 when you diagonalize the Hamiltonian, and that mixture is of the order of epsilon. This is what we have here. So it's 10 to the minus 3. In the first approximation, you can just say that K1 and K2 have definite masses. Now another important point is to, what I was saying, to establish what is really the dominant mechanism between these 2. And the way we are doing is the following. We study decay of K meson into 2 pints. So there are 2 modes, K plus, K minus, and pi plus, pi minus, and 2 pi zeros. If this mixing operates mechanism, then you have the following. K, let me put KL, or which is approximately K2. So that can be transferred to K1, and then we will have decay without CP violation, pi plus and pi minus. And also we will have K short, so that's mixing. Here is epsilon. This is of the order 1. And this is K1 gain. And, no, sorry. Yes. And then it will be pi 0 and so pi plus and pi minus. Pi plus and pi minus. Right? So this is with CP violation. And CP is violated here. And what we can compute the ratio of gamma of decay rates, KL to pi plus pi minus over K short to pi plus pi minus. The same final state, and that you can find notations as epsilon eta plus minus moduli square. So introduce such a parameter. So upper is with CP violation. This is without CP violation. And this eta is of the order of epsilon. Now, we can do the same for pi zeros. So that we can again compare decay rates for KL into pi zeros. And here is K short. And that's what we denote as eta 0, 0 moduli square. Now the point is that if this mechanism, wire mixing, is the only mechanism of CP violation, so let me see what I can delete. You have already this picture. So if this is the only mechanism of CP violation, then one would have eta plus minus equals eta 0, 0. And so a precise expression is for this 2.3 10 to the minus 3. So it should be exact equality if CP originates only from this mechanism. One can see this in the following way. Let me write probably still these diagrams. So we can write schematically this as KL, sorry, epsilon, K1, pi, and moduli square, which can be written as product of KL equal to K1 moduli square, and then K1 and then K1 decay into 2 pi's moduli square. So what happens that this is, and I will divide when I compute eta, continue. Then eta plus minus moduli square equals I need to divide this onto K1. So probably I can probably even skip these things and to say immediately. So this is what we have in denominator when we compute plus minus. This is staying in denominator, right? And therefore eta, which is ratio of these two, is just given by by this KL go to K1 moduli square. Let me see if you. So what is here? I'm computing first of all this matrix element squared, and I can factorize it. So this is the first part, and so this is the part without CP violation. When I compute eta, I need to divide this product onto just this part, right? And so they cancel, and what I have is just this transition. But this transition is the same for decay into pi plus, pi minus, and pi 0, pi 0. And therefore, I'm getting this equality of eta plus minus or moduli and eta 0, 0. Questions? Should I do this slower?
Here we will have only one, or we will have in the denominator also Ks go to K1.
So yeah, so because this Ks is approximately K1, okay? So Ks,
Oh, I see, because of the
Ks, and this is 1, huh? Go to K1. Let me be more detailed. Okay, what's the question here? So I have this for K short, and then for K short I will write the following. That will be K short 1 K1, which is which is approximately, so it's just 1. So that this what is and it will be, so that will be with just 1, and then divided, essentially that's approximately very good precision, it's just K1 into 2 pi's moduli square. This is because this is 1. Yeah. And so this part and this cancel. And then I will have this expression. I can repeat the same for decay into 2 pi zeros, and I will get that I have the same eta 0, 0 moduli square, and therefore I have equality of these two eta. And finally, so people did measurements, and what they have found that there is some small inequality in this eta plus, minus, and eta 0, 0. And this inequality is parameterized in some funny way. So we are writing eta plus minus is epsilon plus epsilon prime, and eta 0, 0 is epsilon minus 2 epsilon primes. But you can parameterize it anyway, right? So what matters is difference. So in general, these are complex parameters. And what has been found is that real part of epsilon over epsilon prime, so epsilon prime over epsilon equals, and let me give you this, the experimental result is so the final experimental work average, that this is 16 plus minus 16.6 plus minus 2.3, and here 10 to the minus 4. And these guys made the theoretical computations, and theory standard model is something like 15 here. So there's very good agreement. Although, say, a couple of years ago, people had another predictions from the standard model, which deviates let's say 2, 3 sigma from experimental result. So epsilon prime describes the difference of these two eta parameters. Questions?
How can we relate that to the CP phase in the CK animation?
Well, so this direct measurement shows from triangle diagram. So it's not box diagram, but it's through triangle diagram. So that, this is how that diagram also depends on mixing parameters. Okay? So now we are switching to continuous symmetries. Parity, C-parity, and CP, where I should add also that Cronin and Fiji got a Nobel Prize for discovery of CP violation. Okay, so next topic is U1 symmetries. The transformations are the following. You have field Fi. Under U1 it gets a phase factor, which is I. Or maybe I should put here J, not to confuse with alpha. And here's Fj. And conjugate is transformed with minus EQJ alpha F J. So alpha is continuous parameter. Qj is some number which is characteristic of a given field Fj. So if in your theory you have several different fields, then they can be transformed with different parameters Q. So Q is characteristic of a given field, a corresponding particle. Okay? So in general, transformation is written as I, Q, J, alpha. And this is unitary transformations. U dagger is 1, clearly. So this U1 is also diagonal transformation, which means that it doesn't mix the fields. So it transforms field into itself with additional exponential factors, additional phase factor. This means that the different transformations with different alpha commute. So if you have U alpha 1, and then transformation with U alpha 2, it's U alpha 2, U alpha 1. So this is a billion group. If I have several fields in my theory, they can be transformed with different parameters Q, and so I can write that F1, Fn have the following infinitesimal transformation. Let me write this for small. If alpha is small, then I can put this as 1 plus I Q qj alpha. And so this transforms as I alpha parameter q1 qn and f1 fn. So this is the form of infinitesimal. It should be 1. Okay? The form of infinitesimal transformation. So that can be considered as a generator of transformations. And this is diagonal. A generator. And as we discussed before, if we have the diagonal generator, then parameters which are staying along the diagonal characterize the particle. Essentially, this is what I was saying already before. So now let me go to quantum level. So this is at classical level. So at quantum level, we have transformation of the following form. And I put here dagger because it's unitary transformation, unless it's f prime. And the u can be parameterized as exponent I q alpha. And so q is actually is operator. And it should be Hermitian. To have u unitary. Now we have consistency with classical transformations. If you say that u fj u dagger equals exponent I qj alpha fj. So we have correspondence with classical if the action of u or on operator f, we get this expression. From here we can get how the fields are transformed. So what we are doing is again considering infinitesimal transformations. And in this case u is 1 plus q alpha. So and I can insert into this expression this expansion. It will be 1 plus I q alpha fj 1 minus I q alpha, and that should be 1 minus I plus q small j alpha and the field fj. Right. So when I open these brackets and neglect the term which is proportional to alpha squared, what I will get is q fj minus fj q equals q j f j. So I also cancel I and alpha parameters. Okay? Now, if I act by this expression onto vacuum state, I will get the following. If vacuum is invariant under transformation, then this term vanishes because here I have operator acting on this field. do you understand why? So Q acting on 0 is 0. Do you know why it is? So the point is that if I'm acting by U operator on 0, and if vacuum is invariant, then I should get vacuum again. Okay? So I can write this as 1 plus IQ alpha acting on vacuum, and it should be again vacuum. In the case of symmetry, if vacuum is invariant. So what I will get? The first term, 1 cancels with what is on the left-hand side, and I will get Q acting on vacuum gives me 0 for any alpha. So transformation itself doesn't change vacuum, means the generator of transformation, which is staying in the power of this exponent, it vanishes vacuum. Therefore, from this equality, I'm getting that Q acting on Fj gives me Q Fj, right? Because Fj acting on vacuum give me the state of J. And again, the story is the same, and it should be J, that this equation can be considered as a equation for eigenstates and eigenvalues of operator Q, and then Qj's are eigenvalues of operator Q for the state Fj, and therefore these parameters Qj can characterize a given state. So let us consider system of the fields. And the state is created by acting of by operators on the field on the vacuum. And let us see how this combination is transformed under U. As before, we can insert here U dagger U in between of each field, U dagger U, and also here U dagger U. And if vacuum is invariant, what we will get eventually is the sum I Q J J F1 Fn acting on vacuum. So here I will have the product of terms U F1 U dagger, which gives me exponent I Q I alpha. Well, it should be alpha, right? And the field itself. For consistency, to put J everywhere. And therefore, each of these factors will give me these exponents, and therefore that will produce this with plus sign. Questions? The conclusion from here is that Q is additive quantum number, and the quantum number of the system is the sum over Qj. So the state with the system of the fields is transformed under U transformations with Q, which is equals to the sum of the Q's of the fields involved. Well, I'm moving a little bit fast because I'm assuming that you somewhere already learned this, right? Finally, if our Lagrangian or Hamiltonian are invariant under these U1 transformations, then using the same analysis which we did before, you can find that that leads to conservation of total number Q. That is Q total initial equals Q total of final state. So let me just sketch. I don't want to repeat this because this is a common. You use invariance, which is U, H, U diagram is H. This is invariance, and then you take this in between initial and final state, and as we did already before, you are eventually coming to this equality. You need to take this in between final and initial state. And then inserting this unit as usually we are doing, which is U diagram, then you get that matrix element is non-zero only if you have equality of charges in initial and final state. So now let me discuss applications of these U1 symmetries in particle physics. Well, in general, our Lagrangian depends on many different fields. And usually, such a Lagrangian is invariant under several U1 symmetries, so that the total symmetry can be U, say, 1 times U, B. 1 times U and 1. And in general, you may have such a transformation for each the field. So in general, you may have n factors of this time. You may construct the theory Lagrangian which has n number of U1 symmetries, which equals a number of the fields. So which means that you can make independent transformations of each of your field, and your Lagrangian may be invariant. So a given U1 symmetry, say AU1, from this series of the symmetries is fixed by charge assignment. For the fields. That is assignment of this Qj, which we have discussed. It may happen also that different parts of Lagrangian have different symmetries. The consequence of introduction of this symmetry is that they can forbid some transitions in Lagrangian, some terms in Lagrangian. Now U1 can be global symmetry when parameter alpha, and now we have many of these parameters, so we have say n small n symmetries, and we have a alpha, so alpha a, alpha n. And if they are constant, they do not depend on point x, then we are saying that this is global symmetry, if parameters of transformations do not depend on coordinates. So if they do depend, then that is local symmetry. So gauge symmetry is example of such a symmetries. And in the standard model, we have U1, which is gauge symmetry, apart from SU2. So the symmetry of standard model is SU2 cross U1, and this U1 is hypercharge symmetry. So that is a local symmetry. Let me give you examples of charge prescription, and you will tell me what are these symmetries. Let me introduce charges for proton, neutron, U quark, D quark, neutrino, electron, W plus, for instance. So let me make the following charge prescription. 1, 0, 2/3, minus 1/3, 0, minus 1 plus 1. So what is the physical meaning of this symmetry? So what does it mean? So these are these parameters Q, right, which I have discussed, as Q parameters for different fields. So this means that proton is transformed as I1 alpha, just alpha, so in this way. And U quark is transformed as I 2/3 alpha U quark, etc. So what is this symmetry? What is the physical meaning of this symmetry? You have Lagrangian, which is functional of these fields, and that may be symmetric under transformation. U1 transformations of the type I have written on this right-hand side with the following charges. So what is this symmetry? What is the physical meaning of this symmetry?
Conservation of charge. Conservation of charge.
No, but meaning of the symmetry. Electric charge, right? So this is U1, which describes the electric charge. Wow, electromagnetic, right? And Lagrangian is invariant under such transformations. So now let me give you another prescription. 1, 1, 1/3, 1/3, 0, 0, 0. So what is the physical quantity? What this prescription corresponds to? What is the physical meaning of this symmetry transformation? This is baryon number. So now what is this? 0, 0, 0, 0, 0, 1, 1, 0. So what is that? This is Lepton number, right? That prescription would correspond to Lepton number. So what I have shown before, you will ask me, so that corresponds to U Q, U1, times U baryon number, 1, times U Lepton number, 1. Yeah.
I was confused when we conclude that the quantum total number of different fields conserve because, and it's additive, because if we take the Lepton number for the electron and Lepton number for muon.
Yeah. So that's characteristic, and if your electron or muon do not transform to anything, then that is conserved.
I mean, but if the electron, for example, transfers to muon, and we have like we don't give them flavor, so we have only here one Lepton number from electron.
Mhm.
We have there one Lepton number but muon.
Yes.
We say from that equation that it's conserved. It does not relate anything. So
Well, we will not. I have not discussed total lepton number, because before we have introduced electron lepton number, muon lepton number, and tau lepton number, right? Particular. That is not conserved if you have such a transition, because you have violation, in this case, both electron lepton number and muon lepton number.
Yeah, I see.
And if you have such a transition, of course. Now, what is conserved here is total lepton number. I will discuss this a little bit later. So we introduce also total lepton number, which is the sum of lepton numbers. So I and I is E mu tau. This is conserved in such a process. Total lepton number.
So, and we give flavor for that Lepton number. We distinguish them.
Yeah. So this is for a specific lepton numbers. This is what we call flavor lepton number, if you want. But on the top of this, we introduce also total lepton number.
And that's the same symmetry.
Yes, right. So here, for instance, if I'm introducing, I can specify here, I can put here electron neutrino. Then that will be Le. Now, what is conserved is total. What kind of U1 symmetry gives us that total lepton number is conserved, but total in the following sense. So, okay, probably I understand what is confusion. So we introduce this U1 symmetry, and in general, that means that there's a conservation of, and I have some charge of total charge, so Q initial total equals Q initial up to final total, right? So that's a general. I have not even specified here what is the physical quantity. Now, if Le is conserved, then I can introduce total electron-lepton number, because I may have several leptons in initial state. Like, for instance, I can have scattering of electron neutrino on electron. Right? If I have scattering of electron plus electron neutrino, right? Suppose I have such a process, and it transforms in everything else. Lepton number of this guy is 1. Lepton number of this guy is 1. And I can introduce Le total, and that will be 2 for this process. And it is this which will be conserved. Okay? The same is for muon. So, for such a process, muon lepton number, L mu, is 0, 0, and total muon lepton number is also 0. And that should also be conserved if Lagrangian is invariant under the symmetry. This rule is the same for all these kind of quantum numbers we are discussing. For baryon, for lepton number, I can introduce also L mu, L tau, I can introduce total. And even this should be kind of, I need to sum up over all total lepton numbers of each of the particles which is involved. So you see, this example illustrates the following. I may have different symmetries, different U1 symmetries. And for each of these quantum number, so each of these quantum number corresponds to symmetry, U1 symmetry. So for a given Lagrangian, I can introduce several different symmetries. They differ by prescription of charges. Sometimes they may not be completely independent. I may introduce some more different prescriptions, but I should actually, should check if I can reduce, say, one of the assignments to just some combination of other assignments. Then the symmetries will not be independent. Okay? So, for instance, for this, I would put here everything is 0. For total lepton number, I would put here once we started to talk, I would put here 1 and 1. Usually we are not putting L, so better to put not to confuse with total lepton number of the system of particles. Okay. Now let me discuss some of these quantum numbers. And what we know about these quantum numbers. Actually, a very important quantum number is B minus L. You can compute what is so it's just total L, but also we are talking about B minus L quantum number. But this is not independent, because that can be composed out of B and L. So let me talk first about electric charge. So we checked that this is very good lepton number, very good quantum number. It seems it is not violated. The best limit follows from decay of electron into gamma and neutrino. And for this, the lower bound on the lifetime of electron has been obtained. So has been obtained experimentally, which is 2 × 10⁻22 years. So people use stability of atoms, some change of electric charge in atmosphere. So that's the best limit. And this one gives us the test of conservation of electric charge. Now, baryon, quantum number. Also, we haven't found directly the processes with violation of baryon number. So we are looking for some processes, and they include proton decay. Proton can decay into positron and pi0, for instance. So everything is conserved here but baryon number, right? So in the initial state we have baryon number 1. In final state, total baryon number is 0. So all these guys have 0 baryon number. The best bound obtained for this mode is that lifetime is bigger than 1.7 10 to the 34 years. I mentioned this already in some of the initial lectures, and the bound has been obtained by super Kamiokande experiment. And now we are moving to hyper Kamiokande. So probably it will be created in the middle of 20s, so that that will be detector which is approximately order of magnitude bigger than super Kamiokande, and therefore for the same period it can improve this bound by several factor of several, right? It should be square root of the volume of the detector if you have the same time. Okay? Now, some other modes. Of course, proton can decay into mu plus pi 0 in general, right? For this mode, lifetime is bigger than 7.8, 10 to the 33 years. So weaker a little bit because we have muon here. And a very important mode is proton go to mu plus and k0. And the bound on lifetime is 6.6, 10 to the 33 years. This mode, actually why it is important, it is predicted to be dominant in supersymmetric models. And actually this gives a stringent bound on supersymmetric models. The absence of this mode, the non-observation of this mode. There's also mode with neutrino, antineutrino, and K plus. What you can recognize here, in this decays, B is violated, lepton number is violated, right? We have no lepton number in initial state. In final state, we have lepton number. Actually, this is not observed, right? Remember. But what is conserved is B minus L. This combination of lepton numbers is conserved in this decays. Well, this is an important feature of certain symmetries, conservation of B minus L. Notice that in all these decays, baryon number is violated by 1 unit. So delta B is 1. And B minus L is conserved. People are looking for the processes with violation of baryon number by 2 units. Delta B equals 2. An example of this is neutron-anti-neutron oscillations. So what is the signature? You know, the signature is catastrophic because if you have nuclei and you have neutron which is transformed to anti-neutron, then this anti-neutron annihilates with other neutrons, and you will have essentially destruction of the nuclei and emission of a lot of energy, right, if this process occurs. So this is one way to search for this process, just to look stability of nuclei with some catastrophic destruction. Or you can create a beam of neutrons and then to see if there is a transition of the neutrons to anti-neutrons. So both types of the experiments have been performed, and the bounds have been obtained on this mode. Now let me go to lepton numbers. So probably we have discussed already a lot. So we have leptons, nu e, nu mu, nu tau. And we introduced 3 lepton numbers, Le, L mu, L tau. And so we have this prescription. And we can introduce total lepton number, which is the sum over this L alpha. Alpha is E mu tau. And for all these particles, this is 1. But that is characteristic which distinguishes leptons, whatever flavor is, from baryons, for instance. So if this lepton number is conserved, that would correspond to 3 exact symmetries. It would correspond to U1T times U min 1 times U tau 1. And again, this charge means that under, say, U1E, these two guys get exponential phase factors with parameter 1, and all these are not transformed. Okay. I'm skipping this, but you please ask me the question. So the story is the same. So we are introducing the symmetry, this U1, which means that we introduce transformations of the fields, and transformations are given precisely by this charge prescription. And if the symmetry is exact, then these charges are conserved, or the sum of the charges in initial and final state is conserved. The way we are checking conservation of these quantum numbers and the checking if the symmetry is exact or not, searching for decays like mu gamma, I have discussed already, this has not been found, or tau go to E gamma, or tau go to mu gamma, and this hasn't been found, and for instance, tau go to 3 electrons, so P plus and minus and electron, plus and minus, depending on the charge. So if, for instance, it's minus, it will be plus, minus, minus. So these processes haven't been found, and there is a rich program for future searches for these lepton violation decays. So I introduced these lepton numbers for particles, and for antiparticles, of course, they have different opposite charge, right? So for anti-neutrino electron and for positron, these charges are minus. So. Okay? Yeah?
Are all of these violations important for some theories? Or is it
Oh yeah, of course. Yeah, yes. So what does it mean, violation? It means that you need to introduce some terms in your Lagrangian which violate this lepton number, which means that they have non-zero, you have operators in your Lagrangian which have non-zero these quantum numbers. Well, as we know now that these lepton numbers are broken. So, and we have found this because we have found oscillations. We have found oscillations, for instance, electron neutrino to muon neutrino, or muon neutrino to tau neutrino, where all these lepton numbers are explicitly broken. Just in vacuum, we have these transformations, which means that these lepton numbers are broken. But it turned out, amazingly, that in the standard model, the rates of this process are extremely small. Extremely small. I mentioned already, I think for this it's something like branching ratio 10 to the minus 35 or something like this, and we are at the level of 10 to the minus 14, I believe, before these bounds in the standard model. Which means that if you find these processes, it certainly testifies that the model is not complete and we need to add some terms which violate these lepton numbers. So, it is difficult to, at least in the standard model, to find these lepton number violation processes, to discover them. But amazingly, much more probable is transition of, for instance, electron to muon. That we can find. Or mu go to mu tau. This is oscillations. And this is what has been found. So last lecture will be devoted to these processes. Yeah.
Should we search for those interaction from the early universe resources. So maybe it was broken or the physics was different, but
Yeah, so right.
But
I should
how-
say actually, sorry, yes, in connection actually to your question. So it turns out the still baryon number is violated, even in the standard model, due to non-perturbative effects, first. The second is that since we see this baryon asymmetry in the universe, this in connection to your question, since we see baryons but there's no antibaryons, this means that it should be some process which probably produced this asymmetry, and there were these famous Sakharov conditions which say that you can really start from symmetric universe, this baryon symmetric universe. However, the symmetry is developing if you have baryon number violation, CP violation, and departure from thermal equilibrium. You have the processes which satisfy these three conditions. And so in this case, you can produce baryon asymmetry in the course of evolution of the universe. So the answer to your question, yes, it is important for the early universe. Well, actually, this is what we see is probably the result of baryon number violation. What we see around us, right? So there is no anti-students in the hall which is closed, right?
There was a time when baryon number was broken, baryon number conservation, and now it's asymmetry. That's the thing.
Well, in the early universe, that was much more efficient process because of conditions, densities, and what was important, temperatures. So this kind of baryon number violation in the standard model is extremely suppressed at low temperatures. However, at high temperatures, when the temperature is bigger than the masses of W and the bosons, these processes become important, so-called processes with phalerons, with composite degrees of freedom. But anyway.
But in accelerators, they haven't found baryon number.
No.
No.
Well, you see, simply people are looking for the processes, and some anomalous events I mentioned even before, they may probably, and people are introducing some new particles, they may be probably due to some kind of baryon number violation, if it is eventually, if it is confirmed. So there are some anomalous events, and people introduce leptoquark or leptoquark bosons, for instance, to explain this. So those particles violate baryon number. And at LHC, people are looking for leptoquarks. Particles which actually carry both baryon number and lepton number, they decay and they, with violation of baryon number. And produced, right, so since you have this particle. Okay, so finally what I will discuss, violation of total lepton number and the processes with violation of total lepton number. So this is the definition, right? So again, the most important results on this corner of the blackboard. So this is how we define total lepton number. And I will discuss violation of total lepton number. So violation of total lepton number is related to possible Majorana nature of neutrinos. So in contrast to other charged fermions, electrons, quarks, muons, neutrinos may be Majorana particles. And this is what I will discuss now. So Majorana particle, Majorana neutrino means that neutrino coincides with antineutrino. And this means that lepton number is violated, because for antineutrino, you introduce opposite sign of L. So if here is total lepton number is 1, here is -1, then this equality can be only if you have a lepton number violation, total lepton number violation. So let me start discussing Majorana mass terms. Let me say that we still don't know, and this is one of the main issues actually in particle physics, to establish if neutrino is a Majorana particle or not. So let me start with Majorana mass term. So what is this? Remember that usual mass term of fermion, and if still neutrino may be Dirac particle, like all other fermions we know. So the mass term is given in Lagrangian by this expression, right? For fermions, it's mass, and then it's Dirac conjugate, and that's the field. So I'm writing again symbols, but this means it's operators of the fields or wave functions. That can be written in terms of left and right components of the fermions in the following way. So where nu L is 1 plus gamma 5 over 2, and nu R is 1 minus gamma 5, projection operator nu, right? And nu L plus nu right is nu. Okay, I can split my field in two parts, left and right, using these projection operators. And then when I insert here this expression, due to projection properties of left and right, I will get this. Because left times right is 0. Right? So that you have left but conjugate right. So this is what we call Dirac mass term. So in the Dirac mass term, nu left and nu right are independent components. The mass term of this type can be considered actually as a transition between left and right. So we can write the diagram when nu left is transformed to nu right, and this vertex, so to say, is M. And of course we have nu right, go to nu left if you want. So this corresponds to such a term, and this one to this one, right? So you can treat this as interaction or as a vertex with a parameter M. And so left go to right, or right go to left. So what is important that at this transition, the mass term transforms left components to right and vice versa. So left to right. For neutrinos, which are neutral, electrically neutral, and they have no QCD charge, so they have 0 conserved charges, there's another possibility. We can organize right-handed component which is needed to build up mass term, we can use left-handed component, but take charge conjugate. So when you take left component, you have exercise actually, and make charge conjugate, left transforms to something which is right. So it will be new C right. So what you will get here, right component. And therefore you can use, instead of right component here in this expression, charge conjugate left component. So you can build up mass term with just two components. So it's just left component of neutrino. Okay? So the Lagrangian, or mass term in the Lagrangian, can be written as m over 2. And then I'm using left C, and then I use Dirac conjugate, nu L, plus Hermitian conjugate. So, instead of this term, I took this one. Instead of nu right, I'm using nu left conjugate. So this is what is staying. And then this is Dirac conjugate. And this is nu L. And this one will appear as Hermitian conjugate. Now what is important that I put here 1/2. And this is not accidental. This is just to get a standard that m is the mass in the equation of motion. Remember, to get equation of motion, you need to use Lagrange equation, right? When you make differentiation over the fields. When you have these two, and this is essentially nu L, right? Because you have two conjugation, and you essentially, this is what is nu L. And when you do this in Lagrange equation, when you do differentiation, you will get additional factor 2 when you do differentiation. So if I introduce mass term with 1/2 in Lagrangian, that would correspond to m in corresponding equation of motion. So this is what is important. Physical mass is determined by the equation of motion, right? And so then m in this, introduced in this way, is physical mass of the neutrino. This expression can be rewritten as m over 2 nu L transponent C minus 1 nu L plus Hermitian conjugated. And here I used, so, and C, sorry, is I gamma 2 gamma 0 as usually. And here I used explicitly expression for this charge conjugation of fermion field. And then I'm getting such an expression. So that's continuation of this. And T is transponent. So I'm getting this term, which is called Majorana mass term. So what are the properties of this term? First of all, this term is not possible for charged particles. For instance, for electron. I cannot put here electron and here electron, because then the charge of this operator would be plus or minus 2, right? This means that will violate, that will lead to processes with violation of electric charge by 2 units. So, and only for neutrinos I can introduce this term because they are not violating the electric charge in this way. So now we introduce mass for 2-component neutrino. So Dirac particle is 4-component, but we can use only left part and not even introduce right part of neutrinos. So number of degrees of freedom decreases, and still we can introduce mass term. Another point is that we have this nu T nu, and this operator has lepton charge 2. Each of them have lepton charge 1, and therefore such an operator, if it appears in Lagrangian, will violate lepton number by 2 units. So this means that one expects the processes with a lepton number change by 2 units, a lepton number violation by 2 units. Again, so Majorana mass term has lepton charge 2, or minus 2, if it is conjugate, emission conjugate. So, this mass term violates lepton number by 2 units, and therefore it leads to the physical processes which violate lepton number by 2 units. Let me show you that this mass term corresponds to Majorana neutrino. So Majorana neutrino is introduced as neutrino which coincides with antineutrino. So we can parameterize Majorana neutrino as nu plus nu c. And if I use only left-handed components, that will be nu left plus nu c right. So clearly, if I make charge conjugation of this combination, I will get again the same nu m, right? So that satisfies that this is Majorana particle. Mass term for such a particle is given by m over 2 Majorana times nu m. So what I can do, I can insert this nu m in terms of left and this c nu c right components. So what I can write is m over 2 nu left plus nu c right. And here is nu, and this is conjugate, nu left plus nu c right. So again, let's repeat, I use only left-handed components. Now I build up the state which has this Majorana property using this nu c right. So when I do c conjugation, I will get again the same expression. I have this mass term for Majorana neutrino, which is usual, it's like for Dirac neutrino also. But now I'm introducing here, inserting here this expression, which explicitly gives me Majorana property of neutrino. And I will not do this explicitly, you can do this by yourself. One can find that this is reduced using projection properties of left and right, that is reduced to m nu l t c minus 1 nu l and plus Hermitian conjugate, which is precisely the term which we have introduced before. So in this way I have shown that the mass term introduced by using charge conjugate of the same left-handed component is indeed corresponds to mass term of Majorana neutrino. Well, in fact, we can introduce Majorana neutrino in different way. Well, I will not say too much. We can introduce nu Majorana prime, which is nu minus nu c. So here is plus, but I can introduce minus sign. Then under charge conjugation, nu m prime c will be minus nu m prime. So we will have additional sign minus here. And this is the state with opposite CP parity, if you want. So because under C, and essentially this is CP, it changes the sign. So it's another way. Another state. Well, in general, we can even have not just minus, but introduce the phase here instead of plus or minus 1. And this is what is called Majorana phase. And interestingly enough, it has physical meaning and physical consequences. if your neutrino is transformed, Majorana neutrino is defined in this way, or in this way, which is more general because beta can be 0, it can be pi, and therefore you will get different phases. So these phases play and have the physical consequences, which I will discuss. And what are these physical consequences? I will start, probably I will finish this next lecture. Maybe I'll finish it just one page. The way we are trying to establish if neutrino is Majorana particle or not is to search for so-called neutrinoless double beta decay. So what is this? What is usual double beta decay first? Usual beta decay is when you have nuclei Zn, which is transformed to nuclei with 2 times bigger charge plus 2 electrons and plus 2 electron antineutrinos. Well, we can also have the processes when charge decreases by 2 units, then you will emit 2 positrons and 2 electron neutrinos. So this happens if transition to Z plus 1 and is forbidden. And that can be forbidden for various reasons. And one reason is just the masses of corresponding nuclei. There's about 50 nuclei with the following feature, and I will give you example of germanium. So let me put here the mass, and this is the charge. And then it may happen that, as in the case of germanium-76, that nuclei which has electric charge by 1 unit bigger has a bigger mass. So this is actually arsenic. So such a transition, of course, is forbidden. But the next nuclei, which has 2 times electric charge by 2 units bigger, has a smaller mass, and this is selenium 76. So that such a transition is kinematically allowed. Okay? So these types of the decays have been introduced by Geppert-Meyer. In 1936. And that type of the decay proceeds when inside the nuclei 2 neutrons simultaneously undergo beta decay, usual beta decay. So you have 2 neutrons, they are transformed to protons with emission of electron and antineutrino, and the same is here. We have antineutrino and electron. This is according to our standard beta decay theory. Though the process will be in the G Fermi square, the amplitude will be proportional to G Fermi square, because we have G Fermi here, G Fermi here. And so this process is very rare because this is the highest order in the weak interactions. And the typical lifetimes expected for such a process is something like 10 to the 20 years. Nowadays, these processes have been discovered. And actually, some cases, it's even big number of events of this type have been discovered. This in particular is discovered for germanium. Now, if neutrino is Majorana particle, then you may have the following interesting thing. These two neutrinos are not emitted but can annihilate inside the nuclei. So this is because, remember, we have mass term, and the mass term for Majorana neutrino would correspond when you have a new bar, and they are annihilating all this type of a transition. So remember, in Lagrangian, it's new, or new bar. So of course you have also transitions of type of, and we have new and new, or so two neutrinos can be annihilate. So you have this type of the transitions. Therefore, in the case of Majorana neutrino, you have again two neutrons. But antineutrino emitted from this nuclei or antineutrino emitted from this nuclei, they annihilate. And here you have production of two electrons. And here you have protons. And you start with neutron. Here. So the process looks like you have Zn in initial state. And it is transformed to Z plus 2 N plus 2 electrons. So what happens here, you can treat this as annihilation of two antineutrinos emitted from these vertices, or you may treat this as antineutrino is transformed to neutrino, and this neutrino is absorbed in this vertex. So what is important, that in this process, delta L explicitly violated by two units. You see, look at this reaction. You have two electrons in final state, and therefore lepton number is violated. So let me still take 5 minutes. I want to really devote next lecture to oscillations completely. I can write the diagram for this neutrinoless double beta decay. And the following form, I have neutron, neutron, and proton, and these guys are inside the nuclei. So they're inside the nuclei. They are transformed to two protons. Here I have exchange by neutrino and emission to electrons. So what is important, that this exchange here, I have this vertex which is proportional to the mass of neutrino, to Majorana mass of neutrino. This is important. So these are proportional to Majorana mass of neutrino. Now, remember that the state of neutrino, which interacts with electrons, and we have electrons here, in the charge current is electron neutrino. So we have current of this type, right? But leptons are mixed, and we will discuss this explicitly later, which means that our electron neutrino is combination of 3 different mass states, and this U gives a mixture of a given mass state in electron neutrinos. So we discussed already before that Maki, Nakagawa, and Sakata have introduced the mixing of neutrinos, according to which electron neutrino or muon neutrino are not mass states. They do not understand coincide with mass states, but they are orthogonal combinations of different mass states. So what you should do here then, you will get 3 diagrams when you exchange nu1, nu2, and nu3. And then what is staying in the vertex here is U, E, E. And here is U, E, E, right? On the top of G Fermi coupling constant. So therefore people introduce so-called effective Majorana mass of electron neutrino, which actually takes care of all these diagrams. And it is given by the sum over mass states, then UEI squared multiplied by the mass, by Majorana mass. Since you have UEI here and UEI here, it appears in this mass as square. It's important, it's not moduli square. This is square, and therefore all the phases which can appear in this matrix element should be taken into account. And also this mass can be complex in general, and this is related to the phase which I have discussed before. So you can introduce Majorana neutrino with this additional phase. And eventually this phase is reduced to the phase in this mass. Finally, the diagram or the rate of this decay will be proportional to MEE moduli squared. Right? So this is the amplitude, and then probability will be proportional to mass moduli squared. Which means that if you will observe such a process, you can measure neutrino mass, or this effective Majorana mass of electron neutrino. So people are looking for such a decay. For usual 2 neutrino decay, you would expect the spectrum as the function of sum of the energies. It's the sum of the energies of 2 electrons which appear in this decay. And you expect here the continuous spectrum, like in a beta decay, because part of the energy is taken by neutrinos, and you do not observe neutrino, and therefore the sum of the energies of the electrons is not fixed, it's in different events, it has this continuous spectrum. In contrast, if neutrinos are Majorana and you have this neutrinoless double beta decay, you expect the spectrum which is just a line. Because the difference of masses of nuclei which decay fix precisely the mass of energy of 2 emitted neutrinos. So the sum of, if you neglect recoil, of course, so the sum of the energies of 2 electrons is just given by the difference of masses of 2 nuclei. So this is the way how people are looking for this decay. They're taking this endpoint of the spectrum and try to find this peak. So probably the best bound has been obtained with xenon, and xenon 136 has a decay into barium 136. And here the intermediate nuclei will be cesium 136 cesium. So that is forbidden. So that's what happens. And the best bound has been obtained by Kamland experiment. So this is the same experiment which was used before to measure neutrino from reactors, I mentioned once. But now it works as this neutrinoless double beta decay or beta decay search experiment. So they put this xenon inside the detector and see particles emitted from the center, in the central part of this detector. And the lifetime is measured, and the bound of this MEE has been obtained at the level of 60 to 165 milli-electron volt. So this is 0.1 electron volt, this is 0.06. So in electron volts, this is 0.06. And this is 0.165 electron volts. And uncertainty is because the problem with matrix element, nuclear matrix element. So when you compute this diagram, you also need to take into account nuclear matrix elements. So there's a big uncertainty, and so this is the situation. So we are at the level close to what is expected from oscillation experiments, which I will discuss tomorrow. So questions? So this is no 0 new, this is 2 new. spectrum.
This NI that this covers the annihilation of the neutrinos is the M that appears in the Lagrangian, or is the M of the mass states?
Which is the same after some corrections. And high order corrections if you want. So this is the same as in Lagrangian, yeah? And this is the same which appears in equation of motion, which means this is the mass of the state. So if you will make mass spectroscopy and measure this mass by some other ways, and there are some other ways to measure this mass, not only through this neutrinoless double beta decay, by just the end point of the spectrum, then you will find this mass. So the problem here is that in this neutrinoless double beta decay, you measure this combination. It's not just individual mass. Yeah?
We said that mass term can be complex. In the,
Yeah.
Like what allows this to be complex?
So, and you see that is important for this expression because in this sum, you compute eventually moduli square of the sum. And therefore complexity here becomes important. So this is Majorana phase. Yeah, nothing is wrong because in most of the cases in kinematics, it's like a moduli square, and this phase doesn't play any role. It plays the role in this case because you have this interference of contributions with different masses.
So we could also put complex masses in other Lagrangians, but it didn't.
Yeah, you can put for electron, but it has no physical meaning because you never test this. You always have this moduli square. So this is kind of specific case, and the nature is kind to us to arrange this type of the process. Of course, if you study, say, interference of electron with muon, but I don't know, this is a kind of just Gedanken experiment, then that the phase problem, but this is not even Majorana, because always for Dirac neutrinos, you see you have antiparticle and particle. So in your Lagrangian, so you have Dirac conjugate. So you have electron here. So that phase has no physical meaning, but in contrast to this Majorana phase.
Maybe it's better to ask for tomorrow, but do neutrino oscillations somehow, or to what degree imply the oscillations on leptons?
Yeah, that's common question again. If you want, I can elaborate. So in principle, this is possible. In practice, it is not. Let me put it this way. So what was interesting, some years ago, actually in the beginning of 2000, one collaboration, which is Moscow, Heidelberg-Moscow collaboration, has announced the discovery of this neutrinoless double beta decay, which would correspond to this invariant mass 0.4 electron volt, quite big. And for a long time there were kind of enormous discussions and collisions about this claim of the discovery. Now it looks like it's completely excluded. So from time to time people may see kind of the hints. And the problem is very difficult again. Since now the sensitivity is at the level when this peak is actually not so high, it's something like here, something very small. And then what is important, even energy resolution. Energy resolution is extremely important because if you look at the end point, what you see this background from usual neutrino decay, usual double beta decay. And so what you are looking for is somehow peak somewhere here. But due to finite energy resolution of your experiments, you are kind of smoothing everything. And so in the range where you are looking for neutrinoless double beta decay, there is still a number of events from just usual beta decay. So, and of course there are some limitations for this. You need to have very good energy resolution to really pick up the end point of the spectrum. This is very big business. Now I don't know how many are running, and future experiments are planned. I think even until your retirement, still people will do this neutrino as WPDK experiments. Not mine, I for sure, but even yours. The point is that it may be discovered just, next year. It depends on the spectrum of neutrino. We don't know precisely what is the mass spectrum of neutrino. So roughly speaking, I will discuss this tomorrow. But depending on the mass spectrum, depending on type of the ordering of masses of neutrinos, you may have something which can be discovered very quickly and very soon, or it may take years and years and years, maybe 10, 20 years, and developments of new methodics of detection. Okay? Okay, so then see you tomorrow. And I had no time today to show the slides. I will show you tomorrow.